Alright, so let's imagine that we just have a single stage operational amplifier. So we'll just draw a single stage source coupled pair with a current mirror load, which we've said before is a kind of bad op amp. Okay, so we take our output here, put our input differentially into the transistors M1 and M2. We have our current mirror consisting of M3 and M4. Now again, we're going to just model our op amp as a current source. Now again, this is a simple model. It doesn't apply at all frequencies. We're just trying to estimate what happens at high frequencies. So here, we're just going to treat our op amp like a GM. We're going to put an input voltage into the non-inverting terminal, and we're going to add a compensation capacitor to the output here. Now remember, this particular topology does typically have two poles in it. It has a pole due to the output node and a pole due to this current mirror node where we have some parasitic capacitance. And you've solved for that in some of your homework examples. So the goal here, first let's find what our voltage gain is. So our GM generator here is going to cause a current to flow IX into our capacitor, and it will create a voltage across the capacitor, which will be our output voltage. So we know that IX is simply equal to the GM times the input voltage. And we know that the output voltage, Vout, is equal to Ix divided by SCC, which is the same as saying Ix times the impedance of the capacitance. Now we can find an output voltage versus input voltage with respect to frequency that's valid at high frequencies, and this is GM divided by SCC. Now we want to set this equal to our closed loop gain at our unity loop gain frequency. And of course, this would equal omega 2 for 45-degree phase margin. So we could find that CC, our compensation capacitance size, is equal to GM divided by omega 2 times A sub 0. Okay, so these are a couple of techniques that we use that are narrowbanding techniques. In other words, what we're trying to do is make the dominant pole so dominant in this circuit that it separates itself from the higher frequency poles and allows us to use the op amp in a stable configuration up to some higher frequencies. But this is a fairly inefficient technique. So pole splitting itself is very inefficient. Narrowbanding is inefficient, and we're going to start using a technique called pole splitting, where we're going to smartly place a capacitor that will cause the poles to split apart from one another rather than just affecting one pole like we're doing here. So in this case, all we're doing is modifying the output pole, making it a much lower frequency so that it's clearly much more dominant compared to the higher frequency pole. And we will do that in the Wednesday lecture.